Ha! Live from New York, it's Saturday Night Live!
Yeah. Oh, hello. Hey, I guess it's time for our physics lecture. So today, me and my comrade, Dr. Hummel here, shall explain the idea of light acting as a wave rather than as a particle.
Hi, Aaron.
Oh, hey, buddy. What's your name?
I'm Super Pantleg.
Super Pantleg.
Yeah.
What can you do?
I can learn physics.
Oh, okay. Now, this here is light. Now it comes straight on, all the same wavelength, and it comes and hits this slit. And as it goes through, it sort of acts as a wave. Now, it comes through again and hits two slits. Now when it hits two slits, it creates two waves of light. This allows the light to interfere with itself. So if light was a particle, it would just kind of go through this slit and make like a band of light right there. And also through this slit and make a band of light right there. And no light would appear anywhere else. But that's not what happens. When light goes through two slits, it makes two waves, and the two waves interfere with themselves. So when two crests of a wave collide, such as like at this point here, or any of these dots, there is something called constructive interference, where the light gets even stronger in a supercrest. So these different supercrests line up like this and come and hit against a screen where the light collides against the screen. So where there has been constructive interference, there is a maximum, and the light is strongest there. There's light all along this screen, but it's strongest where there's been constructive interference. Now, so here's where constructive interference took place. Here is where destructive interference will take place. So this is where there's no waves at all, and everything cancels out with each other, so that there is very little light here.
Okay.
Now, this is the first equation that Dr. Young came up with. This is the difference between the length that these two lines have traveled. So PMS1 has traveled this far, and then PMS2 has traveled a bit farther. So the difference between these two is m times the wavelength.
What the heck?
Okay. So now that we have this new drawing of the same light traveling through, we can deduce a new equation from Young's first equation.
You're stupid.
These two sides are both the same, so this is the path difference. Sine of theta equals, and we'll call this x. The opposite, x, over the distance. And then you pull the d up, and d sine of theta equals the path difference.
That doesn't make any sense.
Now for Young's final equation, he changed, this was his second equation. Sine theta can also be a different thing. Sine of theta here is the opposite over the hypotenuse, which is x over L. So he substituted sine of theta equals x over L down into this equation. So he put x over L times d into it equals m times the wavelength. So for his final equation he got this.
Let's see if this actually works.
you.